epilogue, lecture part is just to talk about some things, right, that you may find useful. For instance, CMU is coming to the UNZA. So there are two representatives from CMU, Carnegie Mellon University, Africa, right? They have a presence, I think, in Rwanda or something like that. So they're on the hunt. They're looking for potential students. So if you're one of those people who may want to go and experiment with life at CMU Africa, you probably want to attend this session that's going to be there. Yeah, so I mean, and I'm probably going to talk about a few other things that may be of interest to people, maybe not, I don't know. So this is me, I guess, putting it out there that we have a class, right, tomorrow at 18. Okay, so I have a class tomorrow at 18. And I don't know what's happening here. I was not wanting to do what I just did there. Other than that, I mean, I guess we can continue with our discussion. I'm assuming people have had a chance to go through the things we've been discussing. The things we were discussing yesterday, especially that probably very few of you would have had a chance to do that on Thursday or after Thursday because you were preparing for the test or something. So I'm not really sure if people have any questions related to the stuff that we've covered so far. We've been going through slides that outline a broad spectrum of models, right? And so the idea was to demonstrate, to say, when you're executing a data mining project, using a very simple data set, by the way, right? The data set we are using is probably as simple as it gets here. I mean, it's a real-world data set, but it's not as complex as what you'd find if you were, working with the likes of, I want to say, maybe ZRA. ZRA are really big at this, by the way. Not too long ago, they, I believe they not too long ago, they recruited a student, I think. One of the students I work with was recruited by ZRA to work in their. They have an AI unit or something like that, right? And we had a whole host of them kind of come through, and they came through and attended the AI workshop that we had organized. So we had an AI workshop as a pre-conference event. Anyway, so there's that really. Yeah. So I guess this is me saying you probably want to take note of the fact that these things that we've been using, in as much as I've been using a real world data set, but it turns out that it's a simplified data set, if you will. I'm just going to have to politely ask again, can you see me? For some weird reason, I can't seem to see it here on my phone. Can you see my screen?
No, we
Not,
don't.
Doctor.
Not at the moment, sir.
I don't know what I did here. I guess I'll have to stop presenting and start again or something like that, which is a bit old here, but I'll try again. Yeah. There we go. Much better. I can see it now. All right. Yeah. So we've done quite a bit here, and a reminder that in terms of the models that we're implementing here, we started off by looking at we're deliberately implementing new models that take in as input, that's uppercase X, numeric data attributes. Now, this is me telling
Doctor, I can see your screen. I don't know whether others can see it. Okay. Yes, we can now see it.
Okay. All right. Thanks. I want to put it out there, right? To say, in a row, if I was doing this in a real world setting, right? In fact, we've done this, right? I don't use cost workload, right, as the sole input for implementing a model, if you will, right? It just doesn't make sense because you have just two values, 4, 5, in any given year, unless in instances where you have people that are repeating the course and they have a whole bunch of overloads, right? Cost overloads or something. So we were showcasing how you implement these single numeric feature based models just to illustrate how you do this, right? So we went through model number 1, which takes in cost workload, and then all the while we were also explaining these important things here, like the results, trying to interpret the results here, right? As they relate to both the ROC curve, so that's the diagram on your right, and the so-called confusion matrix, which is on the left, right? And then there was mention of the so-called area under the curve. Now, if you notice, when you generate a ROC curve somewhere, yeah, at the bottom here, bottom right in my case, I have a legend where I'm saying the area under the curve is equal to 0.55, right? So there's an explanation of the AUC score, which is 0.55, and then I gave you homework to go and implement a similar model as model number 1, but one that takes in Moodle hits. And then we looked at, again, another single feature-based model, but in this particular case, the uppercase X was actually a categorical attribute, right? What you notice is that the process you go through is the same, right? That 5-stage process I was talking about. The only difference is when you're dealing with, let's say, categorical attributes, for instance, you would have to ensure that you transform the data, right? So we looked at this. So we have a 2-step process, a 5-step process where we start with the data, we split the data, we learn the model. And what I said was that, in fact, before learning the model, I snuck in an additional step in between 2 and 3, right, where you are transforming the data. In this particular case, in the example, you notice that the transformation of the attribute, which is, it's a dichotomous attribute, right? Yes, no. Are you accommodated or are you not accommodated? And so what we do is we can either one hot encode or we can use pd.getDummies. So that's an extra step, a step that we don't we don't necessarily take into account when we are dealing with numeric attributes, right? Unless if you are trying to do funny things like scaling your data, for instance. Anyways, and then we see that step number 4 is you evaluate the model. So it's the same thing here. The evaluation involves some kind of prediction, right? So you run the .predict function, which takes in as input the test data set. Is it your test input features, or rather input features in your test data set. So in almost all the examples we've been using, this is like 30% of your data, your labeled data set. And then we take advantage of the already existing classification underbar function, which produces a nicely formatted report, something that is akin to, well, I've passed it by anyway, but it produces a nice report. And then as a way of mimicking deployment, we just showcase how you'd feed the model a new observation. Okay. Anyways, again, I gave you this as homework. I told you to go and implement a model similar to model number 3, which is model number 4. The only difference is that the number of classes that you have in your input feature, uppercase X, which is minor classification, is slightly more or are more than campus accommodation. Campus accommodation just has yes or no, whereas your minor has slightly more values. It religious education, civic education, mathematics, there's languages like there's French, there's English, and all those things. But the idea is the same. What you do is you have an additional step in between 2 and 3 where you are transforming the data, right? So you're one hot encoding this information. And then finally, what we did yesterday, and I was looking at the recording, I didn't realize that we spent a little over 2 hours doing that. But I wanted to highlight that there's a little bit of extra work required when you're working with text attributes, right? The very first thing you do is you've got to decide how exactly you're going to transform the data, right? There's a whole range of options that you have. We've looked at two options. They both fall within the broader conference, what are called account vectors. So I showcased exactly how you use TF-IDF, right? To build a model, right? A model that takes in as input text, right? So in this particular case, we're saying we do our inputs as part of stage number 1. We read the data. And what I'm doing here is I'm pre-processing it by, transforming or deriving the final exam score, because it's a float. I have got to convert it into a categorical attribute, is it? Because it's a binary classifier, pass or pass, right? Afterwards, we noticed that in this particular use case, we had to drop values that have now entries. So if there's an observation which does not have motivation, we cannot impute values, is it? Doesn't make sense. For the exam, we can impute. We say if you don't have a score, it's a 0. You got a 0. That's a reasonable assumption to make. But however, if there's no entry for text associated with motivation, it doesn't make sense for you to include dummy text, for instance, right? Or an empty text. You're better off excluding it, right? So this is what we're doing here. We're dropping. And incidentally, the reason I'm highlighting the fact that we're dropping this attribute is because if you're trying to draw parallels between this model and the other models, you won't be comparing, like with like here, right? Because the proportion of the data, the labeled data set that you're going to then split into training and testing is going to be slightly different, because we are dropping attributes here. You can work backwards and ensure that there's a bit of consistency. So what you can do is for models 1 through to, I want to say 1 through to 4, what you can do is you can initially say, I'm going to drop everything that doesn't have survey major motivation and the final exam score, so that it's a lot easier for you to compare these different models, right? But the process is the same. So we pre-process. I'm pre-processing here. After we process, we split our training data, our labeled data set into a training data set and a test data set, right? Again, we're using a 70-30 split, this particular case, which is pretty trivial. And then in terms of transformation, we do the things we were doing when we're looking at those count vectors. Is it for TF-IDF, we have got to create an instance of TF-IDF vectorizer. I'm creating, I wanted it to be slightly fancy here. I wanted to exclude stop words. So at the bare minimum, what I'm saying is that for these entries that we have here, if I have for these entries in the dark here, but I'm not complaining. For these entries here, right? For these, I want to remove things like to, things like there, right? Yeah. Things like M here, because these are stop words at the bare minimum, right? And this is not really a complex corpus. It's as simple as it gets here. It's a very simple corpus. So I'm feeding just one parameter to TF-IDF vectorizer to say, I want you to take into account, English stop words. And then what I do is, you notice here, I'm creating, I want to fit and transform the corpus. Now, you notice that the fit and transform is being performed on the training data set. Yeah. So in other words, right, what we are doing is we are saying we are going to assume that the corpus that we're going to use to learn the model is associated with the training data set, right? So we fit and transform, we create a vectorizer here, right? Instance of TF-IDF, and then we fit and transform using the training data set, the X, the input. And then afterwards, take note, right? We are not fitting and transforming the test data set, but rather we are transforming it. And the idea here is we want to transform, in other words, we are transforming the text that is in the test data set using this vectorizer that has already been fit using the training data set or the corpus, which makes sense because ultimately you're going to train the model based on this thing here. Okay, so we do that. Just take note of the fact that initially we fit transform, and then when we're working with the text, right, at the test data set, we just transform. So it's that dot transform. Afterwards, we then create an instance of multinomial naive Bayes. Multinomial naive Bayes, and I gave you an explanation, is it, for why we're using, all of a sudden, we're no longer using decision trees classifier, but we're using multinomial naive Bayes. It turns out that the different estimators that are available within scikit-learn are associated with specific use cases. And I showed you that map, right? We discovered that the appropriate estimator to use when we're dealing with text input is something that is associated with the naive Bayes, right? Heuristic or algorithm. So which is why we're using multinomial naive Bayes here. So we create an instance of multinomial NB, right? And then we learn the model, is it? So using this classifier, we fit it using the transformed text. Notice we're using this output here, right? We're using the transformed text here, train. But the API works in such a way that it's the same, is it? When you're fitting a model, what you do is you give it two arguments, right? The uppercase X and the lowercase y. Yeah. So we are done. Again, this is it. When you're learning a model, all you do is you create an instance of whatever estimator you want to use, and then you fit the model using your training data set. And then afterwards, you do a prediction, right? So using the same model, we are running the predict function here. But you notice that the argument we're feeding the predict function, it's one argument. In this particular case, it's transformed features associated with the test data set. Now again, this input from the test data set is the thing that has been transformed using this vectorizer, right? Initially created using the training data set. Anyways, so we do a prediction, and then in this particular case, we just wanted to compute the accuracy score. Well, what we do as well is we generate the classification report, right? And lo and behold, in fact, I've slightly updated the slides here to include, in addition to classification report, a confusion matrix or something like that, right? So the code that follows after this classification underbar report here is really just code that is going to enable you to generate the confusion matrix and the area under the curve, right? The ROC curve rather, right? So in terms of the classification report, this is the output, right? Pretty straightforward things. Now, the idea here is at a bare minimum, you want to pay particular attention to this number here and compare it. This is 0.58, right? You compare it with the values associated with what we've done before. 0.58 versus 0.55 for this model number one, right? Anyhow, hopefully this is kind of like making, I think this is making sense really. Yeah, this is making sense here. So for the model that makes use of survey motivation using TF-IDF, what we're saying is that the results, we're looking at your precision required fund scores, and then we have our confusion matrix and our curve as well. Again, what you want to do is when you've generated your curve, for instance, talk more about the confusion matrix here. You pay particular attention to the things that are diagonal here, right? It's the things that you pay particular attention to. For the ROC curve, besides the shape of the curve itself, what you want to do is you want to look at this value itself, the area under the curve itself. And if you notice here, the area under the curve, when we use survey motivation, the text itself is 0.57 compared with 0.57 compared with 0.55, right, for model number one. So usually your comparison is going to take into account all these different key metrics. However, you can, for the most part, when you're building classifiers like this, you can get away with accuracy, right? You're just drawing parallels and you're looking at accuracy. Yeah. Now, just a few notes here about some of these numbers that we are seeing here, right? For the classification report, what we see here is that overall accuracy is 71%, right? This is the interpretation. The precision for pass, and we're just looking at one of the classes. We have two classes here, but the precision for pass we see 73%, and the recall is 77%. And then for the confusion metrics, and I don't know if I regenerated these things here, but and I think this is a bit off here. I'll have to update this. I think when I was generating these graphs initially, I reran this and I got different values. But the interpretation, the initial interpretation was such that the model correctly identifies 24 fail students and 30 pass students, right? And there's a bit of misclassification for 9. I'll explain the confusion metrics just now here. What we're saying is that the ROC curve here, the area under the curve is 0.77 here, which is a reasonable score, right? 0.77 is a reasonable score. Although this is contextual, it depends on the type of problem or task that you're solving. One would argue that if this was in the banking sector where you're dealing with money, people wouldn't really be so happy with this sort of score. But for this particular use case, this is fine. And so what I'm saying here is that as homework, I mentioned this, please look at a bag of words model. So replace TF-IDF with count vectorizer, in other words, right? And then in addition, I don't know if in addition, so there's homework 5B, model 5B is going to use count vectorizer instead of TF-IDF. And what we want to see if the accuracy is going to be any better when you use count vectorizer as opposed to TF-IDF. In addition, as homework, what you're going to do is you're going to combine these features, because all the while we've been using individual features, is it? Moodle hits, course workload. We've used the campus accommodation status, minor, course minors or something. And then we have the motivation text. So the idea here is, can you build a model that combines all of these? And the assumption you'd be making, the hypothesis you'd be making is that a model that combines multiple features is expected or is anticipated to be a lot more effective. Just to give you a sneak preview of what I have done myself, right? When I ran these things on my own, is I sort of scores, right? So I've ordered these in ascending order of the accuracy, which is why the models are not in order. It's 3, 1, 2, 5, and 6. So you see here that the accuracy for the campus accommodation model is 53%. For the course workload model was 54%. For Moodle hits weight, not Moodle hits, but Moodle hits weight was 63%. And then when I use open-ended text from the survey major motivation using TF-IDF, I get 71%. When I combine all of these features, I get 74%, right? So there's the conclusion I'll be able to draw in this particular case is that building a model that makes use of combined features would be better. You understand this? Anyways, what you will notice here when you're combining the features, is that the area under the curve will provide you with a more reliable measure of model's predictive power than just relying on the accuracy alone, right? We see this from combined features. Yeah, AUC score, the last column there. And then we see here, conclusions we're able to draw from here is that if you're looking at single predictors, like single features, we see that the text data, so the survey major motivation, was the strongest single predictor. Is it? Because it has the highest accuracy and the highest area under the curve score, 71% and 0.77 respectively, right? The other thing, another notable thing from this table here is that combining multiple features, multiple data attributes, or using data features has resulted in a better performing model across all key metrics. And in fact, I removed the other things here like precision and recall, but the combined model actually ended up scoring highest in all of the different metrics: precision, recall, F1 score, accuracy, the area under the curve score as well. Okay. Now, I had mentioned just mildly what this confusion matrix is all about. I thought I'd just briefly, maybe now that we've looked at examples of these reports from these models that we've implemented, I thought now would be a good time for us to explain, right? So the idea behind the confusion matrix is it is organized as follows, right? Your rows, your row labels will comprise of actual entries, right? Or labels for actual classes, right? Or labels for values associated with, labels for actual values, right? Because what you're doing with the confusion matrix is you're comparing results coming in from your model with the actual values. And in fact, your comparison is based on where these different column labels and row labels here meet. So you notice here that in this cell here, for us to get the true negative, we are going to be comparing actual fails with predicted fails, right? We'll have this value here. And then in this last cell here, if you notice, we are comparing actual pass with predicted pass, right? So this is a true positive. The idea behind this, right, is that when you're comparing fail with fail, this is a negative output. A fail is a negative output, right? So it's a true negative. Whereas from the perspective of the model, this is a true negative. From the perspective of the model, what is the value that is here, right, will coincide with the predicted pass with an actual fail. So we consider this to be a false positive. Right? The model thinks it's positive, but it's not actually positive because in all actuality, it's a fail. So it's a false positive. Right? And then when we are comparing what the model predicts as being fails when they actually passes, it's a negative, right? It's a negative, but it's a false negative because as far as we're concerned, from the perspective of the labeled data, this is a pass. The model thinks the values here will be fails when in actual fact they're passes. So this is a false negative. And then when we come here, right? When we're comparing actual pass with predicted pass, it's a true positive. So in actual fact, right? When you're looking at the so-called confusion matrix, I guess part of the reason why we call it confusion matrix is because it's confusing, is it? Hopefully not a lot of people are confused about this here. But it turns out that computing things, the values, is usually computing values here, like using a confusion matrix, like the recall and the precision, takes into account these things we have in the cells, is it? Like TN, true negative, false positive, false negative, and true positive. If you remember, when we were discussing this not too long ago, this is 132. Not too long ago, I brought up the issue of true negative and false positive. I like using that graph from Wikipedia. I don't know if you remember this, but I was using a graph from Wikipedia that explains some of these things. It's gone. I don't know where it is also. I thought I had it. I don't know what's going on here, but there we go. There, this. You remember this? At this point, maybe things were slightly confusing, is it? I was telling you that your precision looks at how many selected items are relevant, and then if you look at the formula here, it's like we are taking true positive over true positive plus false positive. So it turns out that using a confusion matrix, you can compute precision and recall. If you look at recall, we're taking the green patch here, which is true positive, we're dividing it with false negatives, right? Plus true positives here. This shaded part here, which is in Anyway, I'm going to go back to slide number 132 or something so that we get back to the confusion matrix. In as much as this thing can easily be, we can easily generate a confusion matrix graphical using matplotlib, but all those fancy things using Seaborn also here. It becomes important for us to understand this thing. I'm going to go back to this graph here. This thing here, right? So pay particular attention to Tn, which is true negative, Fn, which is false negative, Fp, which is false positive, and Tp, which is true positive. I'm going to kindly ask, I don't know, I think Kangwa has his microphone activated here. So if you can mute his. I think there's a hand up from Victor. Hand up here. Probably a mistake, maybe. I don't know. All right. So our definition of these things here are simple. We're saying that a true positive.
He doesn't understand. I don't know why my network disappeared as soon as I raised my hand. So
there's a bit of feedback on your end. We can't get what you're saying. There's noise, I guess. I don't know where you are. We can barely hear you.
Can you hear me now?
Yeah, much better. Yes.
Okay. Yeah, I don't know why my network went as soon as I raised my hand. The question I had was twofold, with the second part depending on the first. So in your confusion matrix, you have a binary output, correct or wrong. What happens if you have a model predict its confidence rating rather than a binary answer, and then you have 0 for I don't know? How do you see that affecting the accuracy?
Sorry, do you want to maybe speak up a little bit, saying what happens if you're predicting?
What happens if you switch from binary yes or no to a confidence rating, and then you have 0 for I don't know? How do you see that? How do you see that affecting the accuracy?
I don't think I understand. I don't think I understand your question here. I mean, maybe we can.
I can elaborate maybe. So we know that many models. I can elaborate a little.
Yep.
Okay, so we know that we usually train our models to give wrong or correct answers. Then we evaluate the wrong answers based on whether or not they were actually wrong. So you've got this thing where does it actually match what the data was? But what happens if your model can say, I don't know? Which would be the 0 output.
Yeah, I think so to answer your question, right? It turns out that so first, your so-called confusion matrix is only applicable to what? Classification, right? I don't know if this is going to answer your question here. So the moment you're dealing with numbers, numerics, you don't use that. And I think I mentioned here when we were discussing evaluation that the only place where you will find a confusion matrix is when you're dealing with actually it's a binary classification or multi-class classification. Because what you're trying to do here is you are trying to, and I've simplified this, right? These examples I have here, you only have 2 classes, but imagine a situation where you have multiple classes. No, I'm going to try and see if I can. Let me try and see if I can find. If I can, I don't know if we have that thing on our website. If there's actually a PDF document, it becomes even more useful when you're dealing with more than 2 classes, right? So you want to predict whether it's an A plus, an A B plus, a B, a C plus, a C, a D plus, a D. So I don't know if
perhaps I may need a clarification.
Sorry?
I may need a specification for specifically when referring to classes. So the output of a guess for a classification is always, is it a confidence rating or is it just a numeric value corresponding to a mapping for each class?
Oh, it would be a numeric value corresponding to a class. So in our case, right? If you remember, what we've been doing is let me just see if I can. I wanted this, by the way. In our example, I don't know if you remember this, but what we've been doing is I don't know if you remember, but we've been doing this, right? We've been saying what we're feeding to the model. We're telling the model that Mr. Model, we want you to have been doing this. What we have, what is generated, and I have code actually in most instances, is it? I have code that again converts this back into a label, because I mean, this is simple for you and me. We know that 1 is a pass, 0 is a fail. You know, but what for this to be visually appealing, we again, I have like simple code. It's an if-else statement. If it's a 1, output pass. If it's a 0, output fail. So the output is usually, it's a number. It has got to be a number. But so if you have classes, those numbers can easily be, I mean, those classes can easily be assigned to numbers. You understand? And you can get away with
Yes.
with
Yes.
something like, oh, this is going to be class 1, class 2,
Yeah.
class 3.
With that clarification, what happens if you replace the simple numeric value with a confidence rating? Then you can still have the compatibility where the model is able to
What do you
say
mean?
it doesn't need.
What do you mean replacing a simple numeric value with what?
The confidence rating. So if it's a pass, it's 0.5 threshold, and if it's a fail, perhaps negative 0.5 threshold.
Yeah. So, but if you have thresholds, you can easily convert them as well. Also, I see what you mean here.
And then the idea is that, so the idea is that, can we make it such that the model doesn't need to get false positive, but rather it can say it doesn't know? And would that increase the accuracy?
No. But you need the false positives, because ultimately when you're generating this confusion matrix, right? You're not going to be using the confidence intervals in this particular case. You'll be using the classes. You understand? So if your model outputs a confidence interval, like you're saying, but you want to generate a confusion matrix, the confusion matrix works with classes. You understand?
Yes. But does that also, but in this scenario, will it spill over to a higher accuracy or no effect on the accuracy itself?
Well, I mean, I don't know. It depends on the problem you're solving, I guess. I wouldn't know. I mean, we would have to look at, that would be on a case-by-case basis. But for this particular, for this particular example, right? We can't use a confidence interval. A confidence, this wouldn't work actually. For this particular example, like a pass is a pass, a fail is a fail. You can't say this range if we have. I don't know what you had in mind by confidence interval for this particular example, though.
Yeah. So on that part where you combine the models, in my head it felt like a possibility to have each model have a specific factor.
Can I ask Victor? This is interesting, but can I ask? There's a bit of background noise as well. We will create a thread, right? Let's exchange emails, and you'll have to answer emails and respond to those emails via email, right? The mailing list, so that we can share or something.
Yes.
Yeah. Great. Wonderful questions there. So just to mention here that these things you're seeing, TP, TN, FP, FN, and TP are defined as follows. So a true positive is a correctly predicted pass in our case. True negative is a correctly predicted fail, right? A false positive is a wrongly predicted pass, right? The model thinks it's a positive when it's a fail, right? It's also called a type 1 error. And false negative is a wrongly predicted fail, right? And then we see here that when we are dealing with, from the perspective of confusion metrics, we actually compute precision and recall, right? A reminder here that for precision, in our case here, if we're looking at, I guess it would be the pass class, we'll be answering the question of all the students we predicted would pass, what percentage actually passed? And what you see here is that you're just computing this very simple expression here: true positive divided by true positive plus false positive. And I showed this visually, but from the perspective of a confusion matrix, you're getting TP and FP. So in other words, you're going to get TP divided by this plus this, right, for you to get your precision. Pretty simple. And then you recall, if you remember, for this particular example, is answering a simple question of all the students who actually passed, what percentage did our model find, right? Because it turns out that the model is typically, unless if it's really one of those nice models, right? Or you've made a mistake where you are testing with the training data or something. So we're asking a question of all the students who actually passed, what percentage did our model find? And if you look at the mathematical expression here, we are going to get the ratio of, again, true positive divided by true positive plus false negative. True positive plus false negative. So in other words, we are getting a ratio of TP divided by this, right? And it turns out that as much as I'm showcasing an example of the pass class, you can do this for the fail class using the same method, is it? Because let me just you can do that using the same method or something like that. And I've really messed up this thing here. So for the pass class, what we are doing is we are using this. Oh, I don't know. This is not show notation tools, please. There we go. So we are getting, for the precision, we are getting a ratio of this true positive divided by true positive plus false positive, and then the recall is going to be this positive and false negative plus true positive. This, right? And you notice all the while here we are interested in things that are associated with the pass class. Is it pass? Here. Anyhow, here, not there, right? And then really just to mention here that the F1 score is just a harmonic mean, and we showcased the formula previously. Anyways, and then the graph, right? The other thing I've focused here is the graph, the ROC curve, is it? And we see here that what the graph does is it plots your true positive rate against the false positive rate. Now, the way it's normally generated, right? And I hope we did this, by the way, in this this paper that I wanted to showcase. This was done a while back, and I opened this primarily because I want to demonstrate how complex, not really complex really, but how useful a confusion matrix can be, right, when you're dealing with multiple classes. So in this paper, we have this, right? We had 11 classes that we're dealing with. Each of these 11 classes, right? But the things that are correctly predicted are things in the diagonal, squares, if you will, here, right? They're located here, and if you notice, it's almost like you are putting values, or you're picking these values where there's an intersection between the classes, both for actual and predicted. So ED here versus ED here, right? Yeah, hope this makes sense. I wanted to showcase this. And then for the ROC curve, I don't know where it is here. I hope I I graphed this a long time ago. It's like 2019, I think it was. There we go. I think I did. No, I didn't. I don't have a dashed line, which is fine though. Also, I don't have a dashed line. But what I was trying to say in essence is that for the rock cave and the area under a cave score, in essence, what you're dealing with is you're dealing with a graphical plot that illustrates the diagnostic ability of a binary classifier. Key thing here is that you only use rock caves when you're dealing with binary classification. Okay. So what you're doing really is for the rock cave, you're plotting the true positive against the false positive rate. Yeah. And then typically you'd have a dashed line. For some weird reason here, I guess my thinking was that this would infer, I don't have a dashed line, but it's supposed to be a dashed line here. The dashed line will represent a model that is no better than any random guessing. In other words, it's like a midpoint, right? Because this area under cave, the maximum can be 1. So you're looking at 0.5. And the idea is when you're you're interpreting these rock caves, right? A good model's curve should be far away from this line, above the line. And if I'm to go back to here, yeah, I don't know if it's crazy model here, but well, I would argue that it's above the line here. But maybe the one we did before is much better, right? So we're saying a good model should be above the line, above the dashed line, right? And typically the dashed line would be a straight line here, is it? And you can tell here that all of these models, most of these models we have okay models, right? With the exception of if you look at when we're using number of pages, it looks like it's no better than the diagonal line that would draw here. Anyways, so there is that, right? Then you have the area under a curve. You can go back to where we were at here. Again, in terms of interpretations, you'll find this in literature. You get a score that's a perfect score, right? It's a perfect model. Not possible. I mean, in theory, it is possible, but in the real world setting, it is not possible for you to get a 1. I always be less than 1. And then if you get an area under the cave that is 0.5, we're saying it's a useless model, is it? It's equivalent of what we are saying, a model that is no better than in random guessing. Generally, right, acceptable models should have an AUC of somewhere around 7 and above, 0.7 and above, in essence. All right, so just quickly here, I thought now would be a good time as any for us to just briefly talk about multi-level classification. You know, all along here, if you think about it, the problems we've been looking at, the models we've been implementing, do 2 things, right? They're supervised machine learning models, and they are predicting categories, right? But they are predicting either exactly 2 categories, or more than 2 categories, right? So the models we've been implementing can be used in instances where you are predicting exactly 2 categories. In all the models, sorry for the confusion here, all the models we've implemented predict exactly 2 categories. But the approach we've been using assumes that we can implement models that can predict either 2 categories or more than 2 categories. We can use the same approach and modify, right? Modify our model such that they're going to be predicting A, B plus, B, C plus, C, D plus, D, probably even an F. I don't think an F. I don't know. Also, we can tweak it, and the only thing we'd have to do, right? We just come here and we write a function that throws through here, right? We go through this. final examination, right? So that, in fact, it's a few in here with a 0. So that it just throws through here, and then it's going to be assigning an A plus, an A, D plus, D, or an F, or something like that. And we don't have to change anything. However, there's another type of classification, right? So what we've been looking at is binary classification. This would be multi-class classification. What I can do is I can also include an example of the fully implemented model to try and see how good of a model we can come up with, a model that takes into as input all of those as we've been combined features model, but it's not a binary classifier. It's actually a multi-class classifier. It tells us whether a student is going to get an A plus, an A, B plus, a B, or a C plus. It's not really going to be as accurate, in part because of the size of the data set, right? If you think about it from the perspective of stratification here, it's like if you think about it, they've told you that your I don't know if this is going to make sense here, but I want this to make sense. They've told you something here. They've told you that they've told us, I guess, I don't know. They've told us that if a score is, and I don't want us to be writing functions that are going to be outputting A plus, B plus, and all that garbage here. I just wanted to, I don't even know here. This is so sad. Grading. I don't know why my computer, I just worked on it, but it's this other idea pad, it's slow. I wanted this. Anyway, this. So in essence, what we'll just have to do is we'll just write a simple function. It's if else, right? And then else is it. If the score is greater than 90, A plus. If it's between 80 and 89, A, and stuff. So that you come up with these labels. And then question from Victor here, those labels would have to be assigned. A plus would be a 1, A would be a 2, all the way up to D or something. 1, 2, 3, 4, 5, 6, 7, 8. Right? So 1 to 8. So that when we learn this model and we are predicting, we are running inference on our model, if we get a 1, we'll know that is an A plus. If we get an 8, it's a D or something like that. If this is making sense. I don't know if this is making sense. So the point I'm trying to put across here is that, yes, Dave has a question.
Yes, sir. Going back to the decision and the report, can you get me?
I can barely get you, but I can get what you're saying. Yes.
Yeah. So our model is suffering from insufficient data. So I noticed the recall for some levels. We have like 5 levels. The recall and the precision is like 1, and some is like 0.9, but for the others like 0.0000. So now, according to what I was
So you'd have, it's probably an issue of data imbalance, right? So you have an imbalanced data set, and what you can do is during your demonstration, you state the limitations that you have. There's probably a reason why you're getting those scores. So we expect you to, in your report and in your presentation, state the limitations, the reasons why you're getting those scores.
All right, thank you.
Yep, great. All right. So bring us to a discussion of this other type of supervised learning. Is it we mentioned from the outset that we can work on a problem or a task that helps us predict a value, right? That's regression, and we're not really going to get regression, sadly. or we can work with a model that classifies either of two classes, a binary classifier, yes, no, pass, not pass, fail, not fail. Or we can build a model that outputs multiple classes. This is digit 1, 2, 3, 4, 5, 6, 7, 8, 9, right? If you look at one of the data sets that is in this that comes bundled with the scikit-learn library, right? Or you can actually build a model which it outputs multiple values, multiple labels. And if you remember at the very beginning, I gave an example of Stack Overflow, right? Where a question can be tagged with different labels. In fact, forget about Stack Overflow. Imagine a situation where you want to tag comments on Zambian Watchdog. You want to tag a comment as being political, right? Maybe you want to tag it as an insult or something like that. Maybe it's business related. It turns out that if you go through, some comments can be associated with multiple things, right? It can be both political and it could be an insult there, or it could be sarcastic, or it could be business related, right? It could be current affairs or business, I don't know, right? So enter the world of multi-label classification, right? So what we want to just briefly look at here is how we build models, multi-label classification models, right? So again, what we've done so far is we've been working with single labels, but we want to look at a case where we are working with multiple labels, right? Typically, the task you solve with multi-label classification is such that a sample, an observation that you run inference on can be associated with none of the labels. It can be associated with just one of the many labels you have, or more than one label, right? So an example, for instance, you can have the news article that's political, it's associated with economics, and maybe it's tied to politics or something like that. Now, when I was making changes to this, right, and Davey and his group are the ones that prompted me to do this because they're working on a problem that is associated with multi-label classification, right? I've had to make modifications to the data set because in its current form, the data set doesn't really, it doesn't have an attribute that will enable us to do this, right? So we're going to be still analyzing the survey major motivation data attribute, and then try and see if we can assign multiple labels to the text. So in other words, the task we are solving is we want to see, we are no longer interested in just predicting students at risk of failing, but rather we've noticed that there's a whole range of text, right? I hope you'll be able to understand the hypothetical problem we are addressing here. Notice that there's a lot of text that is coming in from the students, is it? I don't know what this is here, right? I love computers, and ICT has always been by my heart and something. Comprehend our computer environment, to learn about computers and stuff. It turns out that we want to see, right? Can we figure out what these texts are all about? Can we assign labels to this text? Can we build a model which, when we run inference using a new comment from students, it would tell us to say, well, this comment is associated with this theme, right? And so what I did was I came up with hypothetical themes here. Relative to interest, I'm saying the text, the piece of text can either be tied to technology, it can be linked to something that is career-centric, right? Maybe somebody wants to find a job or something, or personal interest, right? Somebody is just doing this because they have a genuine interest in computers or to acquire knowledge. So in other words, we've defined this hypothetical. I actually use just keyword matching really to build this quickly, right? So we want to build a model that will assign these tags to a comment, so that when we have a comment like this, the question we'll be answering is, should we, colleagues, iLock, should we assign this piece of text here? I'm interested to know computer functions and be able to interact with it. What is this, right? Is this associated with technology, career, personal interest, or knowledge, right? So first I defined in the notebook I will be sharing. You'll notice that first I defined these keywords, right? And then for each theme, I'm creating a new data frame. And I'm using a very simple function. You find these things in the notebook here. So the idea really is, and this is a code here, but the idea is to come up with something like this. The idea is to come up with something like, come on, why? The idea is to come up with something like this, where for each, horrible stuff, for each record, right? I'm just going to get the first one so that you see. iloc 0. I'm going to transpose this. It doesn't matter. So for each, why am I even transpose this? I guess I may have to transpose. It's not even working. So what I'm saying is that for each piece of text, I have created a labeled data set that I'm saying for this first one is associated with technology, personal interest, knowledge acquisition, right? So I've created another data set, in other words, right? Okay, this is what the code does here. All of this is associated with just, kind of creating this newly created data set that we're going to use here. Now, what's particularly important here is to get an appreciation of the fact that the way we learn models, multi-label classifiers, is different from, multi-class classifiers and binary classifiers, right? For you to build a multi-label model, multi-label classification model, you typically need to use an approach like one versus rest. It's called the wrapper in scikit-learn. I want to refer to this as an approach because you can also use what are called classifier chains, right? There are a number of approaches. And those of you, again, who were paying attention, will remember that this thing came up in one of the, I want to draw attention here to this. Ooh, is this the one? Institution reports? No. Is this? This thing came up again, right? When I was, but these guys, they didn't upload. When I was showcasing an example of a project we worked on with, we do a lot of conference papers, so finding that needle in the haystack here may be a bit of a problem here. Is this the one? This thing we call, I hope there's beautiful. So what you remember at some point, I was giving an example of experimentation, right? This thing that I'm about to show you came up, right? And I was telling you to say, one of the factors we did when we were building this multi-label classifier, I hope this is the one here. I think it is also. One of the, oh my goodness. Beautiful. One of the things that came up is, you remember I said one of the factors was the way we're implementing this binary classifier. You can use what's called binary relevance. You can use classifier chains, or you can use one versus rest. Now, one versus rest happens to be one of the simplest implementations when you're building a multi-label classifier. So I'm trying to justify here in this slide, right? You say you can use one versus rest classifier. The idea behind how this works is that you identify, you try to separate binary classifiers for each label. So in our case, implicitly what we're doing, if you go through the code afterwards, we'll be building binary classifiers for technology, career, personal interest, and knowledge. Simple. This is as simple as it gets, right? Yeah. If you're wondering, why are we doing this here? Well, the standard classifiers, the status we've been looking at here, are designed, right, for a single label. Yes, no, pass, fail, A, B, C, or something, right? One, either of one, right? So they can't directly predict something that can both be yes or no, simultaneously. So we are using one versus rest in this particular case as an approach, right? It's a strategy that works in such a way that it breaks down your multi-level problem into multiple independent binary classification problems. So in other words, you can view this as being a sort of problem which is going to, there'll be a binary classifier for technology, a binary classifier for career impact, for personal interest, for knowledge acquisition. Simple. This is how this works, right? And this way, it makes a problem more manageable, is it? So you're viewing it from a perspective of it comprising of sub-problems, in other words. Now, I thought I would put it out there that there are other approaches to multi-level classification. There are ways beyond what we are doing here. Like I mentioned, classifier chains and binary relevance. In fact, in a real-world setting, when you're building these classifiers like this, you have to empirically determine which one is better. In our case, ultimately, I think we settled for classifier chains, I believe. If you notice the things that are in bold here, the final model, right? We built a more different sort of models, but some models use binary relevance, some use classifier chains, some used one versus rest. And we discovered that using classifier chains results in a more effective model. So the final model that was implemented and deployed was implemented using this strategy, right? Classifier chains. I thought I'd mention this was complex, really, because if you look at the fact here, it's like what do we use? Binary relevance, classifier chains, or one versus rest? What else? Which algorithm do we use? Random forest, stochastic gradient descent classifier, or multinomial naive Bayes? Because we're working with text here, right? These are the options we had. Okay, we discovered that SGD was better than multinomial than random forest. What else? Must we use term frequencies alone, TF, or should we use TF-IDF? Oh, look at this. It turns out that TF-IDF is the better option. What else? Should we just take into account as the feature? Should we just work with text? Should we work with the abstract? Or should we work with both the title and the abstract and combined? What do you know? The best performing model is one that combines text, the title, and the abstract. So this stuff here. And also something to mention here that the evaluation for our discussion in 4792 makes use of these other metrics we've already discussed, right? F1 score, precision, recall, and accuracy. However, in a real-world setting, you use metrics that are specific to multi-level classification. This is the reason why you're looking at things like Hamming score, the Jaccard score, right? Of course, there's also F1 score. So, anyways, so there are other more complex, methods that you can use, like classifier chains, right? Where you have your classifiers, kind of trained sequentially here. We're not looking at that here. Some advantages of one versus rest, it's quite simple, really. It's very easy for you to understand. Clearly, if I tell you that we can view a multi-level problem from the perspective of it comprising of independent binary classifiers, it's as simple as it gets, right? It's very easy for you to understand because you already understand how binary classifiers work. So it's flexible as well. They can use any of your binary classifiers that are appropriate for binary classifiers like logistic regression or support vector machines, for instance, as your best estimator. You notice for implementation, your best estimator is still going to be one of those estimators that we've looked at using our map from scikit-learn, right? And then again, interpretability is quite easy because you view these classifiers independently, right? So you can easily gain a sense of how they perform independently. Anyhow, and then in terms of building the model itself, you notice that the new things that we're importing from scikit-learn, I want to draw attention here to the fourth entry here. We're importing from sklearn.multiclass. It's appropriately named, aptly named here. We're importing one versus rest. And guess what? If we say, I'm going to say import sklearn, and then if I say import sklearn dot multiclass dot, right? What we are saying is that we are importing one versus rest. Is it one versus one, but one versus rest? Some of these classes I haven't even used here. It's interesting. Anyways, so there's that. And then The rest is the same, right? All the other import statements are the same. Like TF-IDF, because we're going to build this multi-label classifier TF-IDF. If we're using the bag of words model, would have said import count vectorizer, right? And then we have your classification report here. I'm importing logistic regression because I'm going to use this as a base estimator, right? Yeah. Anyhow, we define the features, right? Notice that in case you are confused here, this multi-label DF here is just this data frame, a separate data frame which includes these columns here. Observe this, right? The labels, right, that I've created because the original data frame did not have this, and the text itself, this. And if you want, I mean, for you to be able to look up information, you could have easily included the student ID, but it's not necessary. So it's just a piece of text itself and the labels. The idea behind this is that this is going to be used as uppercase X. These are going to be used as lowercase Y's, the multi-labels. They're the things that we're predicting. Yeah. Anyhow, so we have the features, which is just going to be, if you notice here, survey motivation, and then the labels are all of the 1, 2, 3, 4 labels, right? We split, it's the same thing. Everything is the same in life. We split. After we split, we have got to transform the data, right? The input, because we are working with textual content. Yeah, this. We cannot feed these estimators we're using in this particular case, logistic regression. We can't feed logistic regression this. So what do? We convert to numbers, and we're converting to numbers using TF-IDF. So we import, we are creating an instance of TF-IDF vectorizer here. After we do that, we fit and transform the vectorizer using one training data set. And then we transform, we're not fit and transform the test data set, we transform it. Yeah? Done. And then we specify the best classifier, and I decided to name it as best classifier. It's like the algorithm, the estimator we're going to use, right? For these individual models. Just imagine what we're doing as building binary classifiers, right? 5 of them, I think it is, using logistic regression. All right. And then what we are doing is we're going to create an instance of this one versus rest. But what we're doing is we feed, right? We wrap the base classifier, which is logistic regression here, into the one versus rest. Yeah. And the rest is going to just magically happen. The one versus rest will know to say, I need when I'm taught to train, right? When I'm taught to learn on uppercase X, train. What I'll do behind the scenes is I'm going to look at all of these. I'm going to look at all of these different labels. What do you call this? Technology, career impact, personal interest, knowledge acquisition. It's not that hard. It's simple. I want to mention something here. Do not memorize for this exam, please. Do not memorize the import statements. I will in the exam, if there's need to give you import statements, I will tell you in the exam to say this is where you will find the class, right? Nobody asks those things in programming, so I'll give you context. If there's a question about programming, don't waste time memorizing. How am I going to? The quiz was different here. How do I import one versus rest? Right? I'll tell you. Maybe I'll tell you to say you will find one versus rest in the multi-class module or something of scikit-learn library or something like that. Please don't just focus on the more important things. So you do a wrapper, right? You fit, you train it, boom. Right? Now, if you look at the code, right? What we're doing here is in the code, we first load our text features using our newly created labels, which are these things here, these, right? And then we split the data, we vectorize. This is what we've been doing. We define the best model, the best classifier rather, best estimate as logistic regression. It could have been multi A, by the way, right? And you'd have to empirically do this. What's important though, what sets apart multi-label classification from multi-class classification or binary classification is the fact that we have a part where we need to wrap this base classifier with one versus rest, right, before the training. So the training is only done after you wrap the base classifier within one versus rest. Okay, and everything is done automatically for you, right? In this particular case, the training will be done separately 4 times, so because you have 4 separate binary classifiers. But for technology, 1, career impact, 2, personal interest, 3, knowledge acquisition, 4. You understand? Anyways, and then we then do a predict here. Now, the notebook that I'm going to share with you guys has some nice details. The output, you can run, play it back. I do encourage you to play it back. I will share it tonight. But I thought I would take the liberty to showcase to you the scores, right? So remember I mentioned that in an ideal case, in a reward setting, you'd be using metrics like, there's standard metrics for such problems, such tasks, right? Jacquard score, Hamming score, right? But what we're saying is that we can view the performance, right, of these models relative to the individual binary classifiers. Is fine. Understand? And I think this is what Dave was saying. You notice, Davey, how I'm also getting 1 here. Anyways, and then the summary here in terms of interpreting the classification report is the same because we're using standard metrics here. So nothing to speak of there, right? Listen, I also wanted to just finally here, right, just briefly talk about it. I'm going to sneak this into the notebook. But here's the thing. I will sneak part 4 into the notebook, but pay attention. There will be no question in the exam on and about unsupervised machine learning. I just feel it's important that you learn about this. In fact, what I may do if I find time, I'm going to create a screencast for those that are interested on unsupervised machine learning so that I explain exactly how this works. But I'm just going to look at the theory here so that you have an idea here. K-means clustering. So for unsupervised machine learning, remember we said it's DB scan and K-means clustering and stuff. Well, if you are trying to identify patterns using K-means clustering, there's a few things you probably need to know here. The fact that clustering is really tied to pattern recognition. So this idea that you're working with a data set is not labeled and your interest is to try and group these observations, right, into clusters that are going to be related somehow. What I have on the right, by the way, is a data set that I've been using with a master's course I've been teaching for quite some time now. And we use the JCTR BNNB report statements. What you're seeing here, we decided we're trying to see if we could cluster the BNNB values based on towns, if you will. So the idea here is that there are certain towns, right? JCTR will compile BNNB values for Lusaka, Ndola, Kitwe, Chinsali, Mongu, Livingstone. So the thinking here is that the cost of living for towns like Lusaka and Kitwe would be the same here, right? Because these are expensive places. Whereas if you look at something like Livingstone and Chipat, maybe not Livingstone and Chipat, but Chipat and Mongu will probably be in the same cluster or something. If you notice here, the way it was graphed here is horrible. We shouldn't have had towns here. But notice that we have clusters that are in, I don't know if this is blue here, light blue here, then there's blue and then there's red here, right? You notice there's Lusaka and Ndola are in the same cluster or something like that. So the question is, how do you do something? How do you generate this sort of a pattern, right? Well, again, this is an unsupervised machine learning task, right? It's unlike regression or classification. And just to put it out that there are typically 2 main types of clustering approaches, non-hierarchical and hierarchical. In non-hierarchical clustering, you're looking at a situation where the relationship between the clusters is undetermined, whereas in hierarchical clustering here, repeatedly linked pairs of you have repeatedly linked pairs of clusters until every data object is included in a hierarchy. And in fact, if you read up on k-means clustering, you notice that the way the heuristic works is that you go through several iterations, right? You reassign. You're reassigning these data points, these observations to different clusters until you converge, right? Anyways, so we are, which is why we are saying here that what you find in a notebook, which is k-means clustering, is a classic example of non-hierarchical clustering, right? And the way the heuristic works, I can include maybe an implementation in the notebook for those that are interested. Again, this won't come in the exam, but you select the number of clusters k, and then you set random centroids, right? Central points. The central points will represent the k clusters. It's like a location in your vector space of these clusters, yeah. And then what you do is you start reassigning these data objects to the clusters they are closest to, right? Which centroid are they closest to? And then you go through a process where you compute new cluster centers, and then again you reassign until you get to a point where you converge, right? Now, there's something interesting, right, about clustering here. It's like if you're given a data set, if you're given a data set, right, I want you to plot students at UNZA. Here's SIS data. Create groupings. Maybe, I don't know if it's groupings based on performance or some crazy thing like that. The question is, how many clusters are you going to create, right? Right? What value of k are you going to assign? Well, you could say you're going to be randomly assigning values of k until you narrow down appropriate k, but there's an approach, right? I want to argue that this is a qualitative way of determining the value of k. So you can plot what's called an elbow plot. So you plot an elbow plot on an XY plane where the y-axis is going to be the sum of square errors, and then your x-axis is going to be a number of clusters, right? Number of groupings. And the idea behind the elbow plot is that the point at which, observe, the point at which your graph, your elbow plot, forms an elbow represents the number of clusters you're going to have to build your model. So in this particular case, it's 3. It's weird here. Anyways, I thought that kind of mentioned that here. Now, hope this was sufficient. And then also, in closing, we have a but in closing, I wanted to mention that, you know, anybody can build these models, right? Almost all of you. My expectation is that almost all of you can build a very simple classifier at this point, right? It's like September 13th here. All of you can do this. But the question you should be asking is, how then do you deploy this in a real-world setting, right? Oh, we've built a model, right, that predicts students at risk of failing. How do you deploy this in a real-world setting? I thought in closing, I would showcase how we deployed. And you know, if my other computer was not problematic here, I was going to showcase an application that I've been demonstrating to Zicta, Zambia, sorry, not Zicta, but the Roads Development Agency. We had a presentation there. We also had a presentation at the Zambia Road Safety Trust as well, right? So I put together something quickly because the students I was working with were unable to build a very robust application. So the point I'm going to put across is that careful thinking has got to go into deployment. And careful thinking, because ultimately, when you have a problem where you're saying, I'm detecting potholes, people are not interested in seeing you run YOLO, predict, right? And then it shows you, say, in this video, there's a pothole here. People are interested in seeing something like this, right? Something like this, a web-based application. This is what we built, a web-based application, which behind the scenes, there's a model quite all right. And it's an offline model, right? You run inference on that model by feeding it, let's say, video footage. This is how this is built. And then behind the scenes, in each and every frame, not each and every frame here, but we do keyframes extraction. And then we, I wish I had enough time here, but maybe not. But we do a bit of keyframe extraction to extract from the video the GPS coordinates. And then afterwards, we come up with a mapping tool. So the end result, right? We have an inference model, quite right, that tells us this is a pothole and this is a pothole. But for us to build something useful, we built something that works in such a way that using the results of the inference, we map, right? We're telling somebody from RDA to say, here is a porthole. Here is a porthole. In fact, I've gone a step further, right? This has a lot of moving parts, by the way. There's a module that draws intensities. I wish I could demo this. If my computer was not dead, I was going to demo this, a live demo. I think it's cool myself. I don't know about you. But it works in such a way that it draws polylines, right? Because you better think here. If you're saying you are interested in detecting where potholes are. This is a road, right? RDA maps to Google.com. RDA would be interested in them knowing greatest road from Lusaka to Chipata. Where are the potholes? Now you're not going to draw a map that tells you to say, the potholes are here. I mean, it's nice to have map markers, but you're going to have a thing that is crowded with map markers, right? What we've done in our implementation is we've borrowed on how Google Maps renders. I don't know if you've seen what Google Maps does with traffic. Is it? They'll show you different intensities based on which places have the most traffic or something like that. It turns out, ladies and gentlemen, that this idea of polylines on maps is actually, it's a research problem, right? It's not easy. Some of these things, when you see them, when you're just clicking on Google Maps, you're like, it's easy or something. So in this particular case, right, the way Google Maps works is, if I'm going to Chiwoli or something, I wouldn't want to go to Chiwoli here. I don't know. It drags them. But I know that if you look at here, live traffic here, there are certain portions, certain segments of this road which, have a lot of traffic. And so we are doing the same thing with this. We are drawing polylines to say, in the stretch of Greatest Road from here to Mwami border, right, just before Mchinji, or the Chewas call it Inchinji, right, between here and Inchinji, what we have is a situation where in this stretch, Rufunsa, Agri place, right, you have huge gashes, and so the intensity of the road is going to be critical, right? Whereas the stretch of road between when you cross Rwangwa Bridge, Nyimba stretch, beautiful stretch of road. It's smooth, so it's going to be green. You understand? The point here is that deployment is not as simple as people may think, right? In some instances, it may be simple. In other instances, it may not. But at the bare minimum, you develop an API. And that API is hooked to an application like this, right? This application, by the way, has a lot of moving parts. I'm happy to share with you detailed UML diagrams, which I have. This is just architectural diagram. I have a whole range of sequence diagrams and all that stuff. If you're doing software engineering, I think you probably find this interesting, right? Sequence diagrams for specific workflows, right? In this particular case, the video upload and processing pipeline. And then, the complete use case diagram that showcases the features, is it, in the platform itself. The deployment diagram, the same stuff that people have been showcasing. Now, listen, I'm going to leave you with this, right? Again, a reminder that this clustering thing, I felt bad, right? In fact, I feel bad that we didn't even cover regression. But the beauty with regression is it's similar to what we are doing, only that what you're predicting is not a category, but a quantity, right? I so wish we had time for us to cover, what do you call that? The data mining part. I think that's really interesting. But usually you get to apply those things if you find yourself working for telecommunications companies. We had data mats at Airtel. In my previous life, I think I mentioned I was a business analyst. I worked as a database administrator for Airtel for a very long time as well. But also, I hope this was useful. Tomorrow is 10 minutes, 18 to 18. I promise it will be 10 minutes. I want to give you a sneak preview of what is available out there, opportunities especially. And I want to convince those of you that are thinking of, no, I'm going to take a gap year here. I'll start applying in January. To say, start applying now. I also mentioned tomorrow that attend the info session with CMU, because CMU told us that they actually have funding for students, right? All right. Unless you have any questions, I think we can leave it at that. Somebody was asking here, are we going to have 2 hours again here? No. This is no. This class for 2 hours. No. Okay. Ladies and gentlemen, I will see you tomorrow just for 10 minutes.
Sorry,
yes,
I didn't
David
get
has a question.
what you're saying. Yeah, I didn't get what you said about the CMU thingy. Can you please like clarify on that?
Sorry, can you speak up? I can't hear you. I don't know if it's my. It should be my.
Can you clarify on the? I didn't really get what you said on the CMU thing that's happening tomorrow.
No, it's not happening tomorrow. I'm saying I'm going to talk a bit more about this. CMU is CMU. Here's the thing, people. You want to look up. I'll talk about this also, but CMU Africa tomorrow. I just want to talk to you about some. It's like an epilogue class. It's an epilogue lecture. I'm wrapping. I'm winding down formally. Carnegie Mellon University has African campuses. One African campus is in Kigali, in Rwanda. Right? What they do is they recruit students. And they've told us, by the way, that in the recent past, one of the reasons why they're coming to Zambia, to UNZA specifically, is because apparently there are some students that have passed through UNZA that are good students, right? And so they are trying to recruit people like you. I don't know if it's just marketing, but they claim that people that pass through them will have a chance to, find work with these tier companies, right? So just attend the info session. But tomorrow, the people from CMU are coming on, is it Monday or Wednesday? I'll clarify. I think it's Wednesday, I think. I'll clarify. I think communication will be sent through by the head of department, substantive head of department, Professor Piri, because in as much as I've been attending these meetings, he's the one who is organized, who is going to reach out to you. Attend those sessions. Yeah, tomorrow it's just 10 minutes. We can, because it's 10 minutes, I'm happy to do 10, to do 18, but because it's 10 minutes, maybe we can have it early as well. Can I ask, Ms. Temwani is asking what time? I want to say that I can available much earlier as well also. So if you want us to meet for 10 minutes for the epilogue, much earlier than 18 hours, just let Ms. Mlela or Mr. Chela here no, and then we can have maybe a quick session, maybe 13 hours or even 12 or 14 hours, something like that. So I'm available at 12, 13, 14, so not in between, and 18. Thank you very much, everybody. I'll see you. I hope I'll see you tomorrow. If I don't see you tomorrow, I will definitely see you during your presentations. Prepare for the presentations. I know I haven't out the schedule yet, but schedule is coming before the presentation itself. We are following project team members. Bye for now.